Gnanam Paramam Dheyam. Knowledge is supreme.
So in the last couple of minutes we have seen the definition of algebraic elements over a field, and remember that we didn't only define algebraic elements in a field, but in a general algebra, general K algebra, we have defined the concept of algebraic elements. And as a due course we will see this is more generally definition is also very important. Now before I go on to the characterization of algebraic elements, that is how do you test economically some element in a given algebra is algebraic or not. To test this we need some more concepts which I will develop on the way, but before that I want to give examples of an element which are not algebraic, that means examples of transcendental elements. So some more examples. So first one is, now K is field, arbitrary field, and let me take my K algebra A to be the polynomial algebra Kx, and the element there is capital X. Okay, then in this case what is the substitution homomorphism? Epsilon capital X should be a K algebra homomorphism from Kx to A, but A is also Kx. And what is the map? Any polynomial f, go to f evaluated at capital X, but that is same as f. So that means in this case this evaluation map or substitution map is identity map of the K algebra Kx. So it's identity map, so kernel cannot be 0. So then in this case kernel of substitution homomorphism by X is 0. So X is not algebraic. So therefore also it serves the right name that X is transcendental over K. So in other words, the variables we consider are always transcendental. Okay, so another examples proofs are not so easy. So this I am just noting these examples but without proof. So 2 without proof, but eventually sometime we will try to indicate the proof sometime later or probably in the exercises. So look at now Q, our base field is Q and R is the Q algebra. So this is our field extension, and look at the element there, they are elements called E and pi. E is what is called the Euler number, and pi is connected to the circle, right? This is the ratio of perimeter divided by diameter. Now, a lot of things to be checked. I am not going to go into the definitions of E and pi, but just mention that both E and pi are not algebraic over Q. This is not so easy to prove. Proof of E is relatively easier than the proof of pi, but both of these needs integration theory. And which we are not going to go into this course, but at least what we will actually show is that there are more real numbers which are not algebraic over Q than the real numbers which are algebraic over Q. This statement we will prove it in some course of lecture. Okay, so the third, so these are two examples, and okay, so now we want to find a characterization of algebraic elements. But before that, again I want to give one more example that we will get acquainted with examples of K algebras. So third example, now I take K is our base field and I fix a polynomial capital F. Capital F is a polynomial in Kx, fixed polynomial and non-zero polynomial. So, and that I write it as like this: a0 plus a1x plus a n minus 1 x power n minus 1 plus x power n. So, it is a monic polynomial in Kx. F is non-zero. So, a0 to an minus 1, they are elements in the field K. The degree of F is obviously n, and n is bigger equal to 1, let us assume. So, by the way, any polynomial we could have made it monic because we are in a case of field. So, just if I say F is non-zero polynomial, that is enough. But only thing I have to say that the degree is bigger equal to 1. So, look at such a polynomial, and then I have this operation modulo f, Kx modulo ideal generated by f. So, f is the principal ideal generated by f. That means we are taking all polynomial multiples of this given f. So, these are all polynomials. Ideal generated by f is by definition all g times f, where g is a polynomial in Kx. This is clearly an ideal, and then we go modulo that ideal and then form a new ring. Actually, this is also K algebra. So, just there is also K algebra homomorphism from Kx to this algebra. This is surjective. So, this is a natural map. I just want to remind you that this is similar to what we have studied for integers. So, this is similar to, remember, given any natural number n, we have defined z modulo n. This is from the usual addition and multiplication. We have defined two operations, addition modulo n and multiplication modulo n, which made it a ring. And however they defined, when the difference of the integers should be divisible by n, then they are equal. So, we started using this notation a congruent to b mod n. That means they are not equal, but they are in the same equivalence class. So, here that this is same as writing a bar equal to b bar in z mod n. And actually z mod n, you should think it is a ring Z modulo the ideal generated by n. and then we have a natural map here Z2. This map is any A going to its residue clause modulo n, that is denoted by A bar, and then this becomes a surjective ring homomorphism. And what is the kernel? Precisely all those elements which go to 0, that means all those integers who, when I divide by n, the remainder is 0, that is equivalent to saying the kernel of this map is precisely all multiples of n. So similarly, same analogy I applied to the polynomial ring Kx. Instead of natural number f n, I have a monic polynomial f. Monic degree is at least 1, so that it is non-constant, and then we have gone modulo this polynomial ideal generated by f. And what are the elements here? Elements here are precisely, when do I write this and this? So I will write G and H, two polynomials. I will write this congruent to mod f. Simply mean, this is the meaning is the difference belong to the ideal generated by f. That means the difference of this polynomial, so that is f minus g is some multiple of f. So this is phi times f, where phi is another polynomial in Kx. So same analogy as this. So we get a surjective K-algebra homomorphism, and kernel of this is precisely the ideal generated by f, and this ring is called the quotient ring of Kx, and nothing special about these two rings. So more generally, what we know, this construction we will keep using it again and again, and one would have studied this in a first course on algebra. These are also called quotient rings, or also called factor rings. So what is thing? If you have a ring R is arbitrary ring, but assume commutative ring, and suppose A is an ideal in R, ideal. So last time I told you ideals were usually the first time introduced by Dedekind, and Dedekind was a German mathematician. So he has used his Gothic letters to denote ideals in arbitrary rings. So if A is an ideal in R, then we have this ring R, and we have constructed this new ring R mod A, the same as by the analogies of the above two examples. What are the elements here? Their elements are precisely the equivalence classes when you read modulo A. So that means given any element A here, we read mod this A, denote by A bar, and when do you say 2 A bar equal to B bar? That is equivalent to saying A congruent to B mod A. I use the same notation, but this means, so that is the difference A minus B belong to the ideal A. And now one check that this defines a new ring, and that also the natural map is there. This map is sometimes denoted by pi A. This pi A is a surjective ring homomorphism with kernel equal to A. So not only kernel of a ring homomorphism is an ideal, but this shows also that every ideal is a kernel of some ring homomorphism, and this construction is very useful, and with this you can construct many more rings from a given ring. So this will give us a lot of examples of the rings in general. Okay, coming back to our problem. So I wanted to define, so given a non-zero polynomial f of degree non-constant, that means the degree of f is at least n, at least 1, and if we have written it as monic, we are assuming that we can always do it when the base ring is a field. So it looks like this, and then I have gone to the residue class ring. This quotient ring and factor rings are also called residue class rings. So Kx, and I will keep writing it Kx modulo f, that means modulo ideal generated by f. This is my new K algebra. This is a K algebra. There is a surjective K algebra homomorphism from Kx to this. This is surjective K algebra homomorphism, and this, therefore this x goes to x bar. That x bar I am going to denote as small x. Small x is called the residue class of x modulo f, mod f. And that is x. So now we are debating whether the small x is algebraic over K or not. Now I have a K algebra and I have an element there, and then we want to see whether this x is algebraic or not. So this small x in Kx, this residue class ring, is algebraic over K. That is simple, because what do we need? We need to know what is the substitution homomorphism. That substitution homomorphism from the polynomial ring Kx, polynomial ring over Kx, to this algebra. This is our algebra A. So if you write A, that is this, and I want to know what is the epsilon x. That means what? Given any polynomial g, I have to substitute instead of capital X, small x. But this is same as g of x bar. But remember, this is a K algebra homomorphism. So whether I take the images first, whether I add first and take the image, or take the images first and add, and similarly for multiplication, these two operations are same. So therefore this one is same as gx whole bar. That means reading this polynomial g modulo f, that means take out this means what? What is this? How do you find this? This is, you have polynomial g given, and already we had this f, and that is monic. So I am going to perform the division with remainder by f to the g. So you will get a polynomial q times f plus r, where r is the remainder, and the remainder is either 0 or the degree of the remainder is less than the degree of the dividend. Dividend as degree n. So this is degree f, which is n. So therefore when I read this equation modulo f, I get g bar equal to r bar, because this part will go away because it is a multiple of f. So therefore any polynomial here, it is a bar of a polynomial whose degree is less than n, or maybe 0 also. So in any case, the polynomial f, where do they go? If I take g equal to f, what is g bar then? G bar is f bar, but f bar is f is a multiple of f, so this is actually 0. So g bar is actually 0 polynomial. F bar is actually 0 polynomial. That means, so this simply means the polynomial capital F belongs to the kernel of the substitution homomorphism by the small x. and that means in particular this f is non-zero, because f is non-zero, this kernel of epsilon x is non-zero, and therefore this K algebra homomorphism has a non-zero kernel, and that precisely means that x is algebraic. So, we have seen that how do you get more and more examples of algebraic elements. This is the way to get more and more examples of algebraic elements. Also, the last remark in this example, I want to make stress on this point, that if you look at this algebra Kx modulo f, this algebra may not be a field. In fact, not even an integral domain. For example, if I take k equal to q and f equal to, let us say, the polynomial x square minus x, which is monic, degree is 2. So, this is same as x times x minus 1, and what is then this kx modulo f. In this, our small x, which is x bar, is x bar, and what do we know? F bar, which is 0, but f bar is x bar x times x minus 1 whole bar, but that is x bar times x bar minus 1, which is small x times small x minus 1. So, you see small x times small x minus 1 is 0, but small x cannot be 0. Small x is non-zero in this. This is our A. In A, because small x is 0 means what? That means f will divide x in A, but f is a monic polynomial, and if f divides this x, the degree of x should be more than degree of f, but degree of x is 1. So, therefore, this is non-zero. So, therefore, it is not even an integral domain. So, and also this phenomena, if you carefully observe, this is also related to being 0 or not. So, if a polynomial has a 0, then it will not in general be an integral domain and so on. So, to go a little bit, I want to recall now the concepts of two concepts of ideals, which will make this language more transparent as well as easier to understand. So, two things now which I will need, and then we will go on to the characterization of algebraic elements. So, these two concepts. So, remember we have defined in general ideals in commutative rings. And the model examples of rings we had were Z, Kx. In these rings actually we have all the description for all the ideals. And also we have seen the moment you take, for example, rings like this Zx, polynomial rings with integer coefficients, or polynomial rings over a field but more than one variable. Already it is very difficult to give a structure of ideals in these rings, because in these rings there are non-principal ideals. In this ring all ideals were principal. Okay. So, corresponding to the concept prime elements, or what are called irreducible elements. See, remember irreducible polynomial, we were dealing with irreducible polynomials with coefficients in a field, and they are the polynomials which don't have proper factors. That means the only factors are itself and units. Units in the polynomial ring, we know units are only the non-constant units. In this ring, units are even much less. They are only plus minus 1. So, these concepts gives rise to some ideals. These ideals are very important. So, let me introduce a definition of them, which are direct generalization of these prime elements. So, an ideal A in a ring, in an arbitrary ring, commutative always, is called prime ideal, is called a prime ideal if first of all that A, ideal A should not be the whole ring A, and modulo that means the residue class ring A modulo A is an integral domain. So, the last condition is very easy to check, that is equivalently if a product A times B belongs to the ideal A, then one of them should belong to A. Either A is in A or B is in A. So, this is actually the correct definition of prime element also. An element is called prime if a P divides the product, then it divides one of them, because divisibility condition is replaced by belongs to in case of ideals. So, that those are precisely the prime ideals, and the easy example, the first examples of prime ideals in the ring Z, in Z, prime ideals are precisely generated by prime numbers. This is just a restatement of the definition. Similarly, in the ring, polynomial ring over a field, arbitrary field, they are precisely prime ideals here. Ideals are generated by prime polynomials. What are the prime polynomials? Just let me recall. Prime polynomials are monic, and only factors are, only divisors are a polynomial P is called prime if P is monic, and only divisors of P are some constant multiples of P where A is a non-zero constant in the field. Such polynomials we have, remember, they are called prime polynomials. In other words, they are irreducible polynomials, monic irreducible polynomials. So, they are monic irreducible polynomials. And we have described, we know that if I take k equal to q, there are enough of them. In fact, given any n, there are many polynomials of degree n over q which are irreducible. And but over R they are fewer. Over R the only polynomials are linear ones, linear, that is degree 1 polynomials, and quadratic with negative discriminant, whatever it is. And over C, we only want to prove that the only prime polynomials are the linear one, and this is precisely the restatement of fundamental theorem of algebra, which we have not proved it, but we will prove it soon. So, this is what the prime ideals are very important, and in general we know in these rings there are prime ideals, but in general we don't even know that offhand that given any commutative ring there is a prime ideal. So let me just state it. We will not use much about this, but it is very important. So given any ring, commutative ring R, given any commutative ring A, the set of prime ideals I am denoting by spec A. This is the set of all P. P is now Gothic P such that P is a prime ideal in A. This set is called prime spectrum of A. This is one of the principal objects to study in modern algebraic geometry. So, for example, spec of Z, this is precisely the set of prime numbers, and there is only one more prime ideal in Z besides prime numbers, and that is generated by 0, that is the 0 ideal. 0 ideal is prime in Z because Z is an integral domain. So, this is also prime ideal. Similarly, for this same thing will go for polynomial ring in one variable over a field K, that is the set of prime polynomials in Kx. I use the same notation. Now, I introduce the suffix here that indicate that they are prime polynomials in this union 0. 0 is the polynomial 0 is also prime ideal in Kx because modulo that it is an integral domain. So, this is also prime ideal. So, these are infinite sets, but in general it is not clear whether a given ring has a prime ideal or not, but that is very easy because one studies instead of even a special class of ideals called maximal ideals, and that maximal ideal one proves there is a theorem of Krull which says that given any commutative ring there is definitely a non-zero maximal ideal and maximal ideals are prime, etc. So, this will give you enough flow of prime ideals in a ring to go on our study more and more. This was necessary to introduce because I will want to use some of this modern language in the next exposition. And remember again about the course, this course, though it is very historically a very ancient course, I want to use modern methods to give classical proofs, and that will lead us to more far reaching concepts as well as proofs, and it will open up the subject, and it is still active area of research in mathematics which has tremendously many applications in the other fields. With this I will stop.